Everyone, welcome to the 14th session of Electromagnetic Theory and Interference course. In this session, let us apply the Gauss law to find the electric flux density due to a point charge and line charge distribution, and we will solve a problem based on the same. So now let us recollect what is Gauss's law. So Gauss law states that the total flux through a closed surface is equal to the total charge enclosed by that surface, and this is a detailed relation between the flux and the total charge, where the electric flux density also coming into picture. Okay, we already know that using Coulomb's law we've computed the electric field intensity. So to find the electric field intensity by applying the Gauss law, we must first check whether the symmetry exists in the charge distribution. Once it has been found that a symmetrical charge distribution is present, we can construct a mathematical closed surface called Gaussian surface, and the electric flux density should be normal or tangential to the Gaussian surface in such a way that we have to choose the surface. Okay, now let us see the application where for the point charge how the electric flux density is computed. So the point charge in this case is located at origin, and we are interested in finding the electric flux density at a point P, which is at a radial distance r. So using this we are constructing a closed surface called Gaussian surface, spherical surface here, and we can find that the electric flux density is equal to the other components are not present, only in the spherical coordinates r theta phi dr component followed by ar unit vector only present. So applying the Gauss's law, we can see that the total flux is equal to the net charge enclosed, right? So Q is equal to closed surface integral of electric flux density into surface area. So here we are considering d as dr into ar cap, and this ds differential surface area I am taking into r d theta. Okay, r sine theta, sorry, it is d phi here. So it is this surface area is having the unit vector ar cap, which is normal to that surface. When I dot product dr ar along with this surface differential surface component, ar dot ar will become 1, and I will get in the integral uh, okay, r square sine theta. So 2r are there, r square sine theta d phi, whereas theta varies from 0 to pi in spherical coordinates and the azimuth angle varies from 0 to 2 pi. If I integrate, okay, r square is constant. If I integrate d phi separately and sine theta d theta separately, I will get this 4 pi r square relation, okay, which is going to be the surface area of Gaussian sphere. You can try it on your own, this integral part, and from here we can arrive the electric flux density, that is equal to q divided by 4 pi epsilon naught 4 pi r square into ar cap. Okay, so the electric flux density d vector I can write along the rho axis, right? It is concentrated along this rho axis. So d rho into a rho cap. So already differential surface area along this axis I can write rho d phi into dz into a rho cap will come. The a rho cap dot a rho cap will get cancelled, and I will get d rho, and we will apply the integral. Okay, for phi I will apply 0 to 2 pi, for d is at 0 to l. If I integrate, I will get this answer for surface area of Gaussian sphere, 2 pi rho l, that is 2 pi r h, that is height of the cylinder, into radius, right? And since this d vector has no z component, so it that means this tangential to this to those surface, right? So finally I can write d vector as rho l divided by 2 pi rho, okay, this ll get cancelled, into a rho cap. This is my expression for electric flux density due to infinite line charge distribution. Now let us see one problem. We are asked to find electric flux density at this particular point that we are considering it as r vector, and there is a point charge, okay, minus 5 coulomb at this location 4 comma 0 comma 0 one, that is along the x-axis. One point charge is there, and there is a line charge along the y-axis. Okay, point charge is in coulomb, line charge is coulomb per meter. So total electric flux density is a vector sum of point charge and line charge density, right? So we already know the formula for point charge. It is epsilon naught E, that is equal to Q divided by VE. We already know 4 pi epsilon naught r square. This epsilon naught and epsilon get cancelled, and we will arrive this expression. For AR cap, we are replacing by r minus r dash vector divided by r minus r dash vector the whole cube. Here r is the point of interest, okay, where we need to find the electric flux density 403 minus r dash is a point where my charge is present 400. So if you take the difference, I will get 003. So we are applying the value of q minus 5 pi millicoulomb is 10 power minus 3 into that vector divided by 4 pi the magnitude whole cube. Simplify, I will get the answer in terms of, since x, y components are 0, only the z component of vector I will get, okay, z cap millicoulomb per meter square, because electric flux density is charge per surface area, right? So coulomb per meter square I will get. For coulomb it is millicoulomb here, since we have taken the computation like that. And we have found one part. Second part is I have to find the electric flux density to the line charge disposed. Just now we have seen that formula. It is equal to rho L divided by 2 pi rho into A rho cap. So A rho cap here is r vector minus r dash is nothing but here the r dash is going to be 0. Okay. So if you substitute and find arrow vector, it is a vector divided by the magnitude. So root of 4 square plus 3 square, I will get 16 plus 9, that is root of 25 is 5 here, right? Now if I want to find only the rho value, what I should do, I should take the magnitude, radius I want, okay, the distance or the radius if I want, I have to find. So it will also be equal to 5, right? Rho is the radius of the cylinder. It is not a Gaussian surface. It is not mentioned. So we are finding from the points given. So dl vector, I am substituting all the values. For rho L, it is given 3 pi millicoulomb. So 3 pi into 10 power minus 3 will come there. Divided by 2 pi rho is nothing but here it is 5. Why 25 comes, I will let you know. Here for this arrow vector, it is going to be the vector divided by its arrow cap is vector divided by its magnitude, right? Okay, so 4x plus 3z, because 0 is for y component, divided by 5. One more 5 is there in denominator, so only 25. If I substitute, I will get this answer in millicoulomb per centimeter square. Now I have to add the charge electric flux density. Electric flux density, I have to sum up the electric flux density due to a point charge and line charge. So this is my line charge uh, values for the electric flux density. For the point charge, we have computed in the previous slide. Okay, that I am going to take it and sum it up. Minus 139 minus 0.139 is at millicoulomb, right? That if I add it, I will get this as my result, okay, in coulomb per meter square, microcoulomb per meter square. So I hope you understood how we applied the Gauss's law to find the electric flux density due to a point charge and infinite line charge. And I hope you enjoyed your session. Thank you everyone. We will meet in the next session. Now let us solve one problem based on first Maxwell equation. So here the electric flux density B vector is given in terms of coulomb per meter square. We are asked to find the charge density and the total charge enclosed by the cylinder of this radius, and the Z varies from -2 to +2 meter. So the charge density here represents the volume charge density, and the total charge is Q. We have to find both of it. So we already know from the Maxwell equation del dot D equal to rho V. So we know how a vector will be represented in cylindrical coordinates. Okay, since here also a D vector is given, so let us take, because these points, if you see, it's a cylindrical coordinates points. This is rho, phi and z. So a rho cap plus a phi cap plus a z cap. If I want to find the divergence of this electric flux density D vector, I should know the general divergence formula in cylindrical. So this is the formula. Here, if you see from the given expression, this unit vector is along the z-axis. So we are not bothered about other two coordinates. So we have to just to take the partial differentiation of this z component along with the z direction. So if I do it, do dz divided by dz term only is present, apart from the other rho and phi component, rho and a phi, these components are not present. So it will come, if I differentiate with respect to z, it is rho cos square psi. And they are asked to find the charge density at this particular point. So substitute rho value as 1, phi as 45. So if you know cos 45 degree is 1 by root 2, cos square 45 is 1 by root 2 the whole square. So I'll get 1 by 2, that is 0.5 coulomb per meter cube, because it's a volume charge density. Since we know the volume charge density, if I integral over a volume, okay, over the cylindrical surface area, cylindrical volume, I will get the total charge density. So how will I write the volume integral dV in cylinder? So rho V is given, rho cos square phi, we have computed. Now for d rho it is not a problem, but for d phi, rho has to be added and dz will be there. So rearranging dz, and we are integrating z from minus 2 to plus 2, and we are integrating this cos square phi. I am just changing into 1 plus cos 2 phi divided by 2 d phi. I am integrating from 0 to 2 pi. So this is the limits of my azimuth angle. Whereas my radius of the cylinder, so here one row, another row. So rho square d rho. It is raised from 0 to 1. It is having a radius 1. So if I do the integral of dz, it is z, and here integral of d phi is phi. That is already 1 2 is there, so 5 by 2 plus cos 2 phi integral is sin 2 phi divided by 2, and already 1 2 is there, so 4. So 0 to 2 pi, this rho square d rho will turns out to be rho cube by 3. The limits I have applied. So if I substitute the upper limit minus the lower limit, I'll get 4 over here. Here, actually sine 0, sine multiples of n phi is 0. So this term, obviously this term, entire term will be 0. Now I have to apply for phi. So it is 2 pi minus 0, and already 2 is there. Here it is 1 cube by 3, that is 1 by 3. So if I do the math, I will get 4 pi by 3 coulombs. This is the answer we got for the expression where the electric flux density is given. Right? This is the total charge. I hope you understood. Thank you everyone. We will meet in the next session.